All right, so Istvan is visiting from Umeå University, right? That's, yeah, it's in Sweden, if you didn't know. And he will tell us about how to use extremal graph theory of things in discrete geometry.
Indeed. So thank you very much for the opportunity to speak here. Thanks everyone for joining. So without further ado, let me jump into mathematics. And so the story I will talk about today started with a question of Erdős, just as many in combinatorics, but it was also as in related forms by Purdy and Dirac. The question is very innocent sounding. So we are given n points and n lines in the real plane. What is the maximum number of incidences between the points and the lines? So in other words, what is the maximum number of point-line pairs where the point is contained in the line? So for example, in the picture, you can see n points and 9 points and 9 lines, and a total of 26 incidences. So this question was asked around the 80s, and it was solved not long after by Szemerédi and Trotter. They proved the following slightly more general statement. So let's say that P is set of m points, and L is a set of m lines in R2. Then the maximum number of incidences between the points and the lines is at most some constant times m times n to the 2/3 plus m plus n. So just to make clear, I will use this notation for the number of incidences. So this is the number of pairs of points and lines where the point is contained in the line. So this result is also sharp. So construction achieving this bound was already known by Erdős. He conjectured that this is the best, and Szemerédi and Trotter proved that this is indeed the case. So since the Szemerédi-Trotter theorem became an extremely influential result, not only in geometry, but in other parts of mathematics as well. And the reason for this comes from multiple sources. So first of all, the Szemerédi-Trotter has many powerful applications. One of the most famous of these is the Erdős unit distances problem, where the problem asks that what is the maximum number of unit distances determined by n points on the plane? And the currently best known upper bound n to the 4/3 comes from an application of the Szemerédi-Trotter theorem. So another famous application involves the Erdős-Szemerédi sum product conjecture, where the conjecture is that if you're given a set of integers a, then show that either a plus a or a times a is very large. Then it's so in the evolution of the lower bounds for this conjecture, the Szemerédi-Trotter theorem was used multiple times. But another reason why the Szemerédi-Trotter is interesting comes from the way how it is proved. So actually now it has multiple different proofs. So I know of 2 completely different proofs, but let me give you an idea of the original proof of Szemerédi and Trotter. So proof idea. So the idea of the proof is the so-called cell decomposition. So what this does is that we can show that we can divide the plane into cells, so which are just some convex subsets, so that each of the cells contains roughly the average number of points of your set. So if you have k cells, then you have roughly m over k points in all of the cells. And also, they have the property that not too many lines intersect each cell. So the blue lines are from your configuration. You can also ensure that not too many of the lines intersect each of the cells. So now I will not give you the exact parameters, but you can set these parameters, so you get what you want. And what then you do is you just count the number of incidences within each cell separately, and within each cell you just apply some trivial bound. And it turns out that this suffices. Good. But now in today's talk, I want to discuss some variations of this theorem. So one very natural question to ask is, what happens if instead of looking at R square, the plane, we look at points and lines over some arbitrary fields?
So Istvan, we want to maybe recommend people to look at Elekesh's proof.
Yes.
The Szemerédi Trotter is not the simplest or most elegant.
Yes, so
even though it's really important, this idea.
So I think it was originally by Seikei.
Yeah.
So there is another proof which uses the crossing number of graphs, which is much more elegant and shorter, but somehow this proof is much more flexible in the sense if you want to generalize it, then this is the one that's usually used.
Also a proof with cuts, polynomial partitioning.
Yes.
That's extensive.
So that's roughly the same idea, but you define this cell decomposition using polynomials. So they originally defined this cell decomposition just by choosing a random subset of the lines, but so you can define the decomposition in multiple ways. Yes, thank you.
What was the name of the author you just mentioned?
It's the technique of Guth and cuts, but the proof was in another. It's in my.
So let's talk about this variant. So let's call this the first variant where these point lines in F square where F is some arbitrary field. So I can immediately see that if you take, for example, a finite field, this proof immediately breaks down because this proof is very geometric. It really uses that we are working on a plane. So what can we say when, for example, we work over a finite field? Now, depending on the answer you are looking for, you can either have a very easy answer or you can have a very difficult answer for this problem. And so depending on how you formulate the question. So let me show you the easy answer to this problem. So when I write M and N, I will always have M points and N lines. So now you can prove the upper bound O square root M times N plus M if M is bigger than N. And if M is smaller than N, you just get the same bound, but with M and N exchange. So I will not write it down. Now, where does this bound come from? So I have a pretty smart audience, so many of you probably already guessed, but let me show you the answer. So the main observation to get this bound is just to see that the point line incidence graphs cannot contain K22. The point line incidence graphs are K22 free. So everyone knows what's K22. So yeah, why is this true? Of course, an existence of K22 would mean two lines that intersect in two different points. So this is trivial. But now, after this observation, we can basically just forget about any kind of geometry, any kind of points and lines, and we just ask that what is the maximum number of edges in a graph, in a bipartite graph on M plus n vertices without K22, and then we can just invoke the famous Szemerédi theorem. Which tells us that indeed if we have a bipartite graph with classes of size m and n, and no k22, then the number of edges is bounded by this bound. So this was very easy. But actually, this bound is also sharp. So it is sharp in the sense that if I don't have information about the underlying field F or how the field relates to M and M, I cannot prove a better bound. So in other words, so let's say that we work over Fp, where P is a prime, and we take the set of points P to be just the whole plane. So let this be Fp squared. And now let L be an arbitrary set of L lines. Then we get that M is P squared. Also, the number of incidences between the points and lines is because every line contains exactly P of the points. So this will be just P times M. So which is just exactly square root M times M. So this construction achieves exactly the bound we want. So this is kind of the easy answer. Now the difficult answer comes when we have some information of the field and we have some information how M and N relate to the field. So one of these difficult answers is the Szemerédi-Trotter theorem, but also we have some weaker answers over finite fields. So the difficult. So one of these results is subroutine result of Borgen, Katz, and Tau. Where they prove that if we have that M and N, so let's say that M and N are equal, and they are both less than P squared, P to the 2 minus epsilon for some field epsilon, then the number of incidences is smaller than n to the 3/2 minus delta, where delta is some positive number depending only on epsilon. So in this case, we get a genuine improvement compared to this. And also this condition ensures that we cannot have this counterexample.
Does such a theorem also imply some kind of extremality of the example up there? Like somehow that the points have to be all of Fp squared to get the maximal incidences?
I mean, if you have P square points, you must take basically almost all points. I mean, you don't have more space. So this is the only.
No, I guess what I meant was that, if you get like some fine-grained version of this bound that somehow says that if I took, little less than Fp square, then I would necessarily have strictly less incidences.
So you mean like little o P squared points there? Yeah, I'm not sure about these kinds of results.
Yeah, that's probably, you can take epsilon to be subcons.
I see.
And then delta will depend actually polynomial in epsilon.
Yes.
It's an involved version of the sum product theorem over finite fields.
I see.
Prime fields, yeah.
Yes. So
And it's a paper had mistakes if you read it.
Oh.
So maybe it's good to point out that when M and N
Oh.
so when M and N are really large, so they are comparable to P, then there are actually much stronger results which just use spectral graph theory. So you can show that the number of incidences is roughly what you would expect just by these expansion properties of the point line graph. So this theorem becomes powerful when M and N are really small compared to P. which is kind of the non-trivial range.
What's the best construction known? So I mean, how much can you hope to improve that bound, or what can you hope is true in that?
Yes. I know very little about this theorem, unfortunately, but if you take random things, they will give some good things, I would guess.
I think for prime fields, it might be 2/3. As far as I
Same
know.
as
Might be the same,
Yeah,
but there's nothing better.
the best construction
As far as
comes
I
from the
know.
construction over the years and maybe.
So actually, if your M and M is something like p to the 3 half-ising, then no matter how you take your points and lines, you will have that many incidences just because of the spectral expansion properties of the graph. So in this case, you don't have bad and good examples, you have like one kind of behavior. Okay. Yes, so this was one variant, but another natural variant of the Szemerédi-Trotter theorem is the. Oh yeah, I promised that I don't write here, so maybe let me.
I think you can write it.
Okay, then right here now. Is that what happens in higher dimensions?
No, maybe they don't see.
Yeah.
Yeah, maybe you should stick to it.
Yeah, maybe. Okay. So these are points. So when we look at the incidences of points and hyperplanes. In RD. So now here, immediately we run into some technical issues. So if we just ask what is the maximum number of incidences between points and hyperplanes, it's not a very interesting question, because it can happen that all your points lie on a single line, and all your hyperplanes contains this single line. In which case you get that the number of incidences is just m times n, which is, of course, trivially maximal. So in order to ensure that we kind of avoid this triviality, one can put certain conditions on the points and lines. And here there are different things studies. So one thing one thing that was looked at, so let's now just stick to 3 dimensions, is that what happens if we assume that no S points lie on a line, or no S planes contain a line. So here there is a result of Rudnev, which says that if no S planes contain the same line, then the number of incidences is bounded by constant m times square root m plus m times s. So in this case, we can have a big improvement compared to the trivial bound m times n. So this result, so this is from 2018, and this had some quite powerful applications in additive combinatorics. But maybe let me kind of compare this to what would happen if we just use the trivial covariance theorem. So note that forbidding S planes containing the same line is a bit stronger condition than forbidding a K2S in the incidence graph. So but now if you just ask what happens, so what is the maximum number of edges in a K2S free bipartite graphs with these imbalanced sizes, then the KS covariance theorem gives the bound O square root S times M times square root M. So if you compare these two bounds, you can see that they're not that far from each other. So if S is a constant, then they are essentially the same. So this theorem becomes really interesting when you take S to be large, just to be some function of M or N.
So just if I'm understanding it, there is no dependence on S in the bound.
That's S.
There is S.
Oh, that's M times S. Okay.
Yes, my S is a bit weird, sorry.
And that is multiplication, square root S times M times.
Yes.
Ah.
Yes. But then, so another condition. Now, where should I make some space? Okay, I don't need those. So another condition you can ask that ensures this non-triviality if you just forbid a k as S in the incidence graph. So no k as S in the incidence graph. So this problem was proposed by Chazelle in 1993. And his motivation for studying this kind of point-hyperplane incidence graphs comes from multiple problems in computational geometry. So one of the problems this is related to is the question that how efficiently can you store, or how much you can compress a point-hyperplane incidence graph. So one way to store a point-hyperplane incidence graph is, of course, to just write down all the pairs. But actually, it turns out that you can do better. And one way to do better is to instead of writing the point-hyperplane pairs, you try to cover your graph with a few large complete bipartite graphs. And then when you store the graph, you just write down the vertices of these complete bipartite graphs. And in case you can find a few balanced bipartite graphs, you can save a lot of space in this way.
Can I just understand what this is? So KSS in the incidence graphs means S points and S hyperplanes, where every point, each of these S points is part of all S hyperplanes.
Yes, so this is forbidden.
But how can that means that and it is distinct hyperplanes and you're in 3 dimensions, doesn't it
If
mean
many points are on a line and
they all have to be on the line, right? Then
Yeah,
all these
yeah.
S points will be on a line,
Or-
and then all the hyperplane will all these hyperplanes. That's the only way this happens, right?
Yes, in 3 dimensions, yeah, but in higher dimensions, this can happen in multiple ways. Yes, thank you. Yes, and another motivation comes from the so-called Hopcroft's problem. So there the problem is that how fast can you calculate the number of incidences between endpoints and hyperplanes. And again, there are faster algorithms than the trivial. But then it was, so this is a very well-studied problem, and it was observed by Ericsson that particularly hard instances of this problem are exactly those point-hyperplane incidence graphs, which avoid these KSS subgraphs. So this is some motivation why we care about this. So now we can, again, first look at what kind of trivial bounds we can find this problem. So as usual, let's look at what the Szöcs-Trend theorem gives. So it gives that the number of incidences at most n times n to the 1 minus 1 over s plus n. So when s is large, this bound is quite poor. However, it turns out that somewhat miraculously, you can have here, when you also use the fact that you are a point-hyperplane incidence graph, you can have here an exponent which does not grow with s. So the currently best known upper bound which was proved by Applebaum and Sharir. This is 2007. So if we assume that we have m points and hyperplanes, so no KSS, then the number of incidences is bounded by constant, where now the constant depends on S and the dimension. So we are working in R to the D, sorry, or the mass. So this is bounded by m times n to the 1 minus 1 over d plus 1 plus m plus m.
It's independent of S, that's how.
Yes, so only the constant might depend. Yes, and maybe let me say that here you can kind of consider two different problems. So one problem is where you think of S as some constant, but maybe some very large constant, but still not depending on m and n. And you can also ask the question that what happens when S depends also on m and n. So I will talk about both of these problems, but first I will concentrate on the case where S is a constant.
What is the exponent that you wrote?
Is 1 minus 1 over d plus 1. So when d is equal to 2, this just gives back the Szemerédi Trotter theorem. So then these two are equivalent. And then, so in d equals 2, this bound is also sharp. However, for when d is at least 3, it is no longer known whether this bound is sharp. And the best known lower bound, so let me write this. So which is due to Bani Sudakov and myself, is so that there exists some S depending only on the, so again, so this is a large constant compared to m and n, such that the number of incidences is at least, so now we have two cases, it's at least m times n, the 1 minus 2d plus 3 over d plus 2 times d plus 3, when these odd, and times 1 minus, sorry, this exponent is a bit complicated, 2d squared plus d minus 2 divided by d plus 2 times d squared plus d minus 2.
But basically, in both cases, what you subtract is a constant times 1 over d.
Yes, so when d goes to infinity, this is 1 minus 1 over d, and this is 1 minus 2 over d. So there is roughly a factor 2 gap between the lower and upper bound. And these exponents are really kind of the limit of a natural approach. So if you want to improve this, there needs to be some very new idea. And maybe just let me say a few words about how this theorem is proved. The way it's proved is some generalizations of the SAD decomposition. So you can use polynomial partitioning, but also you can use so-called space cuttings, where you cut your space with the help of your hyperplanes. So all proofs and all proofs of results that achieve any bound similar to this are based on very geometrical techniques. So then the final variant I want to talk about is what happens when we combine these two variants. So what can we say about points and hyperplanes when we look at over any arbitrary field? So write me as so variant 1 plus 2 is the point hyperplanes. In after the T.
Sorry, Ishwan, one quick question. So maybe you already mentioned this, but which one do you think is improvable? Like the upper bound and the lower bound in this KSS free incidence?
It's I would guess both, but no, I mean it would be not nice mathematics if this would be the answer.
No, I'm just saying what is 1 minus
just
2.
whether 1/d or 2/d.
Yeah, exactly.
Okay, okay. So I would guess 1/d is closer to the truth.
Nice.
But I also have some reasons to believe, which you might see in the next couple of minutes, that's why I think it might not be the case. But anyway, so now I'm looking at what happens over arbitrary fields. And in particular, I will consider this condition, so no KSS. So for the other condition, it's maybe good to point out that this bound of root nav, this actually holds over arbitrary fields as well, if you assume something about that m and n are not too large if you are in a finite field. So this somehow is not geometry proof in this sense. Anyway, so let me state what we managed to prove. So this is a joint theorem with Szemerédi. So Benny and myself. So we show that if P is again points, L is n hyperplanes. In F to the D and no KSS in the incidence graph, then the number of incidences is bounded by. So now the bound will depend on the relation of m and n. So let me write that m is equal to m to the alpha. So the bound will depend on what this alpha is. So first of all, we get that when we have a very skewed situation, so where m is much larger than n, then we have ODS OM. So this is in case if alpha is in the interval 0, 1/d. So we have the bound ODS, m to the 1 minus 1 over d plus 2 minus t times m if alpha is in.
You can write bigger if the exponents are so small.
Okay. I promise the next line will be bigger.
No, but what is the exponent? I don't see.
So,
No, the exponent is.
oh, it's, okay. Over d plus 2 minus t. And t, I will write what t is. So if alpha is in the interval t minus 1, d plus 2 minus t over d plus 2 minus t, and t is an integer, 2 up to d. Yeah, sorry for this, but this is the answer, so I cannot really save time. So this is, then it's, the upper one is m times n to the 1 minus 1 over t. If alpha is in the interval, so whatever is left, so t over d plus 2 minus t, and t over d plus 1 minus t, and for the same t, and finally ODS m when m is much larger. So if alpha is yeah, sorry, I thought I ran out of space. No, I write this. So as when alpha is d to infinity. So we get this upper bound, which might be a bit complicated at first, but actually this bound is also sharp. So again, this bound is sharp in the sense that if I don't have information about the field, I cannot prove a better upper bound. Or let me maybe write out what sharp means, so I can get rid of this. So sharp means that for every d, there exists this s. So this s will only depend on the dimension, such that for every m and n, I can choose my field f. So f will depend on the dimension and m and n, and there exists this point set and set of hyperplanes which achieves this bound. So in some sense, this is the kind of easy answer for higher dimensions, but no, it's not that easy just to apply a curvature theorem. And also, so let me maybe try to compare this bound to the bound of Applebaum of Scherrer, because it's a bit hard to see how these two compare. So let me draw a diagram. So here is alpha. So here is this exponent alpha, and let's here write gamma, where my bound is of the form n times n to the gamma. So I want to convert this bound into this form n times n to some gamma. Now I have these points of interest, which are given by these integers t. So this is 1 over d, 2 over d, dot 1. And then the general point is like t over d plus 2 minus t, and t over d plus 1 minus t. Now it turns out that our exponent is actually jumping between 1 minus 1 over d plus 1 and 1 minus 1 over d plus 2. And so at this point, it's 1 minus 1 over d, it goes up, it goes down, goes up, goes down. And in general, at these kinds of points, this is up at 1 minus 1 over d plus 2, and then it goes down to 1 minus 1 over d plus 1. So somehow, miraculously, at many of these points of interest, we actually recover the exact same bound of Applebaum and Scherrer. While in the worst case, we are still not that far off. And for us, this was pretty surprising, because as you will see, our proof does not use any kind of geometry at all. Our proof is very combinatorial. It really relies on just extremal graph theory. So the fact that we could somehow get the same bound, which was only known to be achieved by geometry, is a bit amazing. And this is one reason why I think that maybe that bound is not the right bound, and maybe the Applebaum and Scherrer bound could be improved. However, on the other hand, our bound is stronger in the sense that it holds over arbitrary fields, and over arbitrary fields, it is in D sharp. Am I doing the time? Okay. So now let me try to give you some idea of the proof. So let me in particular show you how to prove this in a simple case when we are just in dimension 3 and m is equal to n. So proof of upper bound for m equals m and d equals 3. So in this case, what we want to prove that the number of incidences is bounded by constant depending on s times n to the 3/2. Okay. Now the main observation of our proof is that point-plane incidence graphs avoid a very simple subgraph as an inverse subgraph. In particular, they avoid the following 3+3 sized bipartite graph. So we connect all the edges except for one edge. So this is just K3 minus an edge. And let me call this pattern pi3. So the claim is that point plane incidence graphs have no induced pi3. So how do you prove it? It's very simple. So assume you contain this pattern so that so suppose you can find 3 planes, H1, H2, H3, and you can find 3 points P1, P2, and P3 so that they form this configuration. So what does it mean? So H1 and H2 are connected all the points. So we get that P1, P2, and P3 are all contained in the intersection of H1 and H2. But these are distinct planes, so H1 and H2 is either a point or a line or an empty set. So in particular, we just get that P1, P2, P3 are on a line. But note that H3 still contains P1 and P2. But so P1, P2 is contained in H3. But then it means that H3 contains the line spanned by P1 and P2, so it must contain P3 as well. So H3 contains the whole line. So this is contradiction. This is nothing complicated.
You're using S equals 3?
No. So I don't use anything about S. This is true for any point plane incidence graph. Yes.
If you're not using anything about S, what's wrong with that?
So now this is the point where I will use some.
Okay.
So after this observation, I can forget about points and planes. So this is all the geometric information I subtracted from my problem. And now what I will prove is just that. So if G is a bipartite graph, on n plus 10 vertices, which contains no KSS and no induced copy of this pattern pi3. Then the maximum number of edges of G is at most. So get a more concrete bound is at most 2 times S times n to the 3/2. So it is now if I prove this, then this finishes the theorem.
Maybe just to answer Avi's question, you could take a complete bipartite graph here, and that would be induced distinct free, and it would have way more edges than this. So that you need some sort of.
Yeah, no, I was really waiting for this lemma.
To write this. So let's prove this. So the idea of the proof is based on the so-called dependent random choice method. So just to give some credit, so this is a method that was kind of pioneered in the early 2000s by a number of authors like Michael Krivelovich, Benny Sudakov, Jacob Fox, Nogalan. And now it's
Well, I mean, they all did it after Gowers used it in the Baruch-Szemerédi Gowers, to improve Baruch-Szemerédi. Then Benny took it and all the others. So they wrote a very powerful survey on the power of this method, but the method was invented by Gowers.
Okay. Yes, it's good to so invented by Gowers and pioneered by the rest of the people. As well, if you don't know what this is, don't worry. So I will give you the full proof without knowing what this is.
A lot of the developments in the sum product theorems evolved from the Gowers proof using this method of the Baruch-Szemerédi bound, which was using regularity lemma, so it was useless. But all the bounds on this, what was mentioned on Urgenkat-Stau, etc., came only using the Gowers bound.
Yes.
So, yeah.
And this, you will see this is somewhat surprisingly simple idea, but somehow you need a different way of thinking to notice this. So this is Gowers' genius. Okay, so let me draw my graph. So here is G. So let A and B be the vertex classes. And now what we will do, we will choose 2 random vertices in A. So let they be V1, V2. So V1, V2, it's a random pair of vertices. Chosen from the uniform distribution on all the pairs. First, we will look at what can we say about the common neighborhood of V1 and V2. So let me denote this set by X. So X is common neighborhood of NV1 and NV2.
Can I say something more general?
Yep.
The dependent random choice is how do you pick a random set of a graph? Of vertices. And in many arguments, you just pick it as random. But if you want some adjacency properties or correlations between the edges in your induced graph, subgraph, then it's what the Gowers' main point is. Sometimes you should choose your set not as a random set, but as a set of neighbors of a random vertex or the intersection of the neighborhoods of a few vertices. And that's a special case.
Yeah, exactly. So exactly that's what we are doing. So let X be the common neighborhood. And now first, let's try to say something about the expectation of the size of X. Yes, so now I will not do the precise calculations, but this is a very simple thing to calculate. You use some convexity, Anson's inequality, and what you end up with is that this is always at least the number of edges of G squared divided by 4 times m cubed. So in our case, this will be at least s squared. Oh yeah, sorry. So we will start with the assumption that the number of edges is strictly greater than 2s. That's 3/2, and then we show that then we can either find KSS or pi3. Yes. I think I maybe want to keep this. Yeah. So the next step, now in X, we want to find two other vertices, U1 and U2.
Sorry, what E of X is the number of edges touching X in just touching it? Or just the size of X, sorry, okay.
So this is the expected value.
Yeah.
So now we want to find two vertices in X such that their common neighborhood is still large. And the way we will do it, we will count the number of bad pairs, so the number of pairs whose common neighborhood is small.
How do you prove that the expected size of X is that? Did you prove it or?
I mean, so you just look at for every vertex, what is the probability that it falls, and you just sum them together. So to say that a pair U1, U2 in B is bad if U1, U2 falls into X, and the size of the common neighborhood is less than, what do I need? Yeah, just S. And let me introduce a random variable which counts the number of bad pairs. And here comes kind of the meat of the argument, is that we can find a very nice bound on the expectation of Y. So this is most. So the way we will count the expectation, we will look at every pair in B, and we will look at what's the probability that they are bad. So we are summing over all pairs, U1, U2 in B. So first of all, note that if the common neighborhood of U1 and U2 is greater than S, then they cannot be bad. So in this case, they are not counted at all. However, if their common neighborhood is less than S, then the probability that they are bad is exactly the probability that they fall into X, so that they fall into the common neighborhood of V1 and V2. But now the common neighborhood of U1 and U2 is at most S. So what's the probability that both V1 and V2 fall into this small neighborhood? So this is bounded by S over N squared. So is this clear? So U1 and U2 needs to be, so V1 and V2 needs to be in the common neighborhood of U1 and U2 but it is small. So the probability that V1 and V2 falls into this is just bounded by S over N squared. But this is great because we have a total of, n choose 2 pairs. So this is equal to n choose 2 times S over N squared. So here we are just overcounting. So we are even counting those pairs. Yes. Yes, this is fine. So here we are overcounting, but this is definitely an upper bound. And so this is less than S squared over 2.
You need inequality there, right? Because you're not counting over all pairs, you're counting over bad ones.
I mean, here you have equality because you are counting over all pairs, but here you have inequality. So I already overcounted. Okay, but now we are almost done. So now it's just some usual probability trick. So we will look at the random variable, which is the size of x minus y. So the expected value of this random variable is now greater than just s squared minus s squared over 2. So this is greater than s squared over 2. So one thing, this immediately, okay, sorry. So this is the expectation. So we can choose this pair V1, V2, which achieves at least this expectation. So there exists V1, V2, such that x minus y is indeed greater than s squared over 2. But now on one hand, this implies that x itself is greater than s squared over 2. Another thing it implies is that not all the pairs in X can be bad. So we also have that trivially that X choose 2 is greater than Y, because we even have that X itself is greater than Y, so this is also true. So this implies that there exists some U1, U2 in X such that and U1 and so that the common neighborhood of U1 and U2 has size at least S. But now let's go back to the picture. So what does exactly mean? So now we have the common neighborhood of U1 and U2. So it on one hand contains V1 and V2. So let's write Z for this common neighborhood. Now both X and Z have size at least S. So if we don't have a KSS, then we must have a non-edge between X and Z. So there exists some sorry for this. So if no KSS, there exists some V3 in Z and U3 in X, such that U3 V3 is not an edge of G. But then we found our pattern P3 because U3 and V3, they have to be different from V1, V2, and U1, U2 because they are all connected to each other and they are all connected to everything on the other side. So then V1, V2, V3, U1, U2, U3 give a copy of P3. And this finishes the proof. So we are now 1 hour in, so would you like to have some break? How do you feel?
It's up to you, but you can ask the audience.
Maybe let's have then a 10-minute break. Cancel the chat. Forget about it.
Yeah, why not?
So now let me say a few words about what to do in higher dimensions.
Just one thing. So just this, like, I mean, this lemma is like, I mean, Poisson law and Tate and Simon's first had, I mean, this dependent random choice argument for proving this induced Covariant-Shorter type things for when you forbid a complete graph.
Yes.
Then we had a paper that was getting n to the 2 minus epsilon when you forbid any bipartite thing.
I will talk about this.
The point of this thing is quite useful for culture.
Yeah, so now let's look at what happens in higher dimensions. The idea is pretty similar. We can find some pattern ID. So let me define what this pattern is, which is then forbidden as an induced subgraph. Since more precisely, it will not be a single bipartite subgraph, but it will be a finite family of bipartite subgraphs. So I will draw it for d equals 5. Or maybe let me just define it in general, and then I will draw it for d equals 5. So we will have vertices A1 up to AD on one side and B1 up to BD on the other side. Yes. So we have that AI BJ is an edge if I is greater than j minus 1, then AI BI plus 2 is not an edge, and the rest of the pairs, they can be either edges or non-edges. So I say that all patterns, all kind of graphs which satisfy this, and whatever the rest is a forbidden subgraph in the point hyperplane incidence graph. And so in the case of d equals 5, it looks as follows. So the first two are connected to everything. So this bipartite graph is symmetric no matter which side you look at. But so the first two vertices are connected to everything. Then this one is not connected to the first one. So maybe let me draw this with red. This one is not connected to this. This one is not connected to this. But they are still connected to everything after them. Yes. So maybe a nice way to visualize this, if you look at the adjacency matrix, this is almost like an upper triangular thing with kind of the corners cut off. So it's not quite that, but it's very similar. And why is this forbidden? So we can do a very similar argument as before. So suppose that this is not forbidden. So let me write AD. It is, so let's say that these are the hyperplanes. No, sorry. So these will be the points. These will be the hyperplanes. So if I can find this configuration, it means that first of all, A1, AD are contained in the intersection of B1 and B2, which means that so B1 and B2 are one codimensional, so their intersection is two codimensional. So this implies that A1, AD are in a D minus 2 dimensional subspace. But now we look at what happens with B3. So B3 does not contain all the points. It does not contain AD. No, sorry, A1. Maybe I messed up the. Yes,
You have to put the labels.
yes, I'm sorry. And then this is fixed. And then, but A1 is not contained in B3, which means that B3 cannot contain this whole D minus 2 dimensional subspace. So in particular, the intersection of B1, B2, B3 so the dimension of this is at most D minus 3. So, but then I still have that A2 up to AD are contained in this D minus 3 dimensional subspace. And I can continue this. So on every step, I decrease the dimension by 1. And finally, what I will get maybe let me still keep this. I get that B1 intersection. So the intersection of all the hyperplanes has dimension 0, which means that it must be a point. But then I still have that AD minus 1 and AB are contained in this intersection, which is a contradiction. So this is why we don't have this pattern. So after this, what we prove is that it's good to have this here. So kind of our main lemma is that again we forget about points and hyperplanes, and we just show that if a bipartite graph on M plus 10 vertices contains no KSS and no induced by D, then the number of edges of G is bounded by exactly this bound, which I will not write up. And this is basically the whole proof. And the way to prove this is that we use repeated applications of the dependent random choice. Of course, it will be more technical, so we have to be careful how M and N relate. So I will not give you that proof, but this is the idea. So now here, let me mention that this kind of lemma leads to this general combinatorial problem that Mattia was mentioning, that so you can ask the following problem. Is that, so suppose that given a bipartite graph H, now let G be a graph. And vertices with no KSS and no induced copy of H. And here you can look at variants where maybe G is bipartite or G is a graph. So now let's look at when G is just any graph. Another question is that with these assumptions, at most how many edges can G have? So at most, how many edges can G have. So when H was this pattern P3 or in general pi d, so this result gives you the answer. But you can of course look at this different bipartite graphs H, and actually many different instances of this problem have been looked at in the past 20 years, but there wasn't really a systematic study of this. So recently we started to look at this problem in more detail together with Alexa Milovich and Zach Hunter and Benny Sudakov. So let me just state what we conjecture. So this is Zach Hunter plus the same author, so Alexa Milovich, Benny Sudakov, and myself. So we believe that the maximum number of edges should be the same as roughly the extremal number of H. So that this number is constant depending on S times the extremal number of N of H. So this is the maximum number of edges of an HV graph on N vertices, where now HV means that just really voids H as a subgraph and not necessarily as an induced subgraph. Because clearly when S is large, when S is say larger than the size of H, then the extremal number of H is a lower bound. So if you have a graph which avoids H and S is large, then of course this will satisfy this property. And we believe that in general this should really control the growth of this.
The intuition is that if, let's say in the case that S is much larger than the size of H, if you contain a copy of H, then you contain an induced copy of H.
Yes, exactly. And so in this paper where we propose this, we proved many instances of this conjecture. So actually already many instances were known. So for example, when H is a 3, it was proved by several authors. Then this question was looked at when we are looking at like string graphs or point box incidence graphs, when H is the family of subdivisions. So Mattia has some results on it with several co-authors. We proved that this conjecture is true for when H is a cycle, assuming the natural conjecture about the extremal number of cycles is true. Also when H is a bipartite graph with a maximum degree on one side, which is again a natural family that studies. So the obvious difficulty in this conjecture that we just don't know this number to begin with. So for most bipartite graphs H, we have no idea what the extremal number is. But maybe this conjecture can be proved with some ad hoc arguments without knowing this number. So there is some hope for that.
In the case that it is proven, do we know the extremal numbers?
So we have a conjecture what the extremal number. So we have a very good idea what should be, and we know that we can achieve the same bounds.
For small values of S, is this interesting? But S equal to 2 or 3, or does S need to be comparable to H?
So when S is small, it can be very complicated what you actually imagine. Because when S is very small, then just the Kőváry-Sturan theorem might give better than this. So then there is this immediate range where we have no idea. And there, so we mostly concentrated on when S is some very large constant.
Yeah, this, I mean, so somehow this is trying to extend the usual to round problems to induced case.
Mhm.
Then you cannot really do that because you can always take a clique as long as your thing is not. So like you want to forbid something that prevents a clique. So you want to forbid as big a KSS so that this is kind of as weak a restriction as you want. Precisely what happened in their picture there, kind of with the S was big compared to D.
So potentially you can, I was just wondering, potentially you can use this conjecture, if you believe it, to disprove Sidorenko.
Does this prove Sidorenko?
if you work for some particular age, maybe you.
Yes, so maybe let me mention just what you also said before, that actually we know that there is an epsilon depending on the age, such that this number is bounded by n to the 2 minus epsilon h. So we know that somehow really h should control this number.
Maybe for non-bipartite age, this number is known. The only unknown case is when age is bipartite.
Yes. But yeah, so what I mean by this is not just the extremal number, but this number as well. So both of this is, yeah. Okay. So now let me talk a bit about the lower bounds. So as I said, this is sharp. Let me show that this is indeed the case. And this might be even more interesting for this audience because the lower bounds comes from some constructions in coding theory. So let me introduce a definition. So I say that a subset S in F to the D is K as subspace evasive. If every k-dimensional subspace, so where subspace means affine subspace, contains less than S elements of S. So these sets appear in coding theories. In particular, they are useful for so-called least decodable codes. So in that problem, question is that you want to send a message, but the receiver might not be able to completely decode it, but instead they get a small list of possible messages. And if you can find a large subspace evasive set with the right parameters, then they can be used to construct these efficient least decodable codes. But now what can we say about the size of these codes? So there is a trivial upper bound on a KS subspace evasive set, which is at most S times the size of the field to the D minus K. So of course you can partition F to the D into these many k-dimensional affine subspaces. So you just apply that each of them has less than S elements. So you get this trivial upper bound. But the nice thing is that when you set S to be, when you think of S as a large constant, this bound can be actually achieved essentially. So there is a result of Beer and Lovett. Such that for every K, so there exists some S, which is at most D to the D, so it's bounded by a function of D alone, such that every sufficiently large field F, there exists a KS subspace evasive set of size at least just the size of that to the D minus K.
So I think that we have a construction of this thing, but I think if you just want existence, I think it's very easy, right? It's like a random.
The random, yeah, random will do.
So random will give you an epsilon which depends on s. So this is a bit better. And yeah, so they actually give an explicit construction, but then so we also showed that if you do the random algebraic method, so you take some zero sets of random polynomials, that also gives you an example of such a set. Okay.
And it uses algebraic geometry, right? Bazooka. Yeah. The only algebraic geometry computer scientists.
Not at the time.
At the time. And then, yeah, the subsequent paper of Evan Shachar with Collar with an algebraic geometry where they use more than that.
Then they use it in the next paper.
Yeah, maybe I don't need this.
We had a talk where you do group theory without groups, only combinatorics. Now we do geometry only with combinatorics, and we need one algebraic geometry.
Without algebra.
Without algebra.
So yeah, we are doing algebraic geometry with combinatorics, but I might not have time to talk about that.
Oh, okay, yeah, sure. You guess what you want, just ask for.
So let me show how to use this to construct these point-hyperplane incidence graphs. So what I prove is that if I have an integer t, which is between 2 and d, then there exists s, and only depending on d. So this will be the same set most d to the d, such that for every prime p, there exists a set p points in fp to the d, where the size of p is p to the t, and there exists a set h hyperplanes where the size of h is at least p to the d minus p plus 2 over s. So such that the number of incidences between p and h is equal to p times h over p, which is omega p, the product of p times h to the bottom minus 1 over d plus 2, and no kss in the incidence graph. So now that this exponent is exactly kind of the extreme values of what we get here. So when the size of p has this nice form, then we get exactly the bound we wanted. And if it doesn't have this form, we can do some kind of interpolation, which leads to the kind of worse bounds in the general case. But this is the main lemma, so this is the only thing I will prove now. And the proof is very simple using these subspace adhesive sets. So I just take p to be v minus t as subspace adhesive. I can take it in size p to the d minus t.
You call the little pq or something.
The what, sir?
The size of the field, can you rename it to q instead of p so it will not look like the other p?
No, it does. I mean, it's a smaller version. Yes, just tell me if you want to know which p is which one. No, so I take n0, so this will be almost the normal vectors of the plane. So this I take to be a t-1 as subspace evasive. And I can take n0, we have size c to the t-1. So now I just do a bit of cleaning. So n0 will be the normal vectors of my hyperplanes, but so I don't want to have two vectors which are just constant multiples of each other to appear. So, but because it's t minus f subspace evasive, I know that n0 cannot contain s points on a single line. So I can find some n subset n0 of size at least 1 over s times size of n0 such that no line, no linear lines, no lines through 0 contains 2 points. Then what I just do is I take H to be the all hyperplanes. The normal vector in yeah, so this is the construction. And why does this work? So let's first look at the number of incidences. So now for every normal vector and every point, there is exactly one translate of the hyperplane with this normal vector which contains this point. So we get this, that this is just the product of p times h divided by p. So this is the bound we wanted, so that's great. So now we just want to show that it's KSS free.
So are you flipping the roles of points and hyperplanes here?
Well,
Because you want p to the d minus t plus 2 hyperplanes.
oh, did I flip? Ah, jeez. Possibly. Yes. Yeah, you're right. Yeah, sorry for that. The idea doesn't change. So just sorry for that. So we show that it's KSS free because suppose that it's not, it means that there exist S points and S hyperplanes such that all the incidences are there between them. But now if we have given S points, they span a subspace of dimension at least d minus t plus 1. So this is exactly the word.
That's the definition.
Yes, because no S points are not d minus t dimensional subspace. And similarly, given H, given S hyperplanes, the normal vectors span a t-dimensional space. Yes, we are the same, but this means that the intersection has dimension less than equal to d minus t. So you see that the intersection is d minus t dimensional, but they contain S points that span a d minus t plus 1 dimensional space. So this is impossible. So we cannot have a KSS. And this is the proof.
Where did the plus 2 come from? And the p to the d minus t plus 2?
There shouldn't be a 2. Where is it?
And then lemma statement.
Second line lemma statement at the end.
Yeah, I probably made a few mistakes. Or I can't read my own writing sometimes.
But maybe just one there, no?
Yes, it should be whatever this gives, because this is like tight.
The bound on the incidence should have d plus 2, but the size of the hyperplane is probably 1.
Okay.
So that's so h, I forgot, so size of h will be p times, so this is roughly p to the t. But yeah, so sorry for that, it's I messed up now with the switch there, but this is the idea, and just you choose the parameters correctly. Sorry for that. Okay. So I still have some time, so in the remaining time I will not do proofs. There is nothing to mess up, so let me just state some of the further results we can prove with these kinds of techniques. So let's get rid of this fast. Says the other question, so I mentioned is what happens when we consider S as not as a constant, but some function of M and N. Or in other words, we say that, okay, we have a point hyperplane incidence graph with many edges, then what is the size of the largest complete bipartite graph you can find? And so let me introduce this notation. So R as G. So this will be the max number of edges in a complete bipartite subgraph. Subgraph of G. So now
You
I'm
really want the number of edges on the number of vertices.
so here I'm looking at the number of edges. So it's a bit different problem. So now I'm not necessarily looking for something balanced, but just something with the max number of edges. Because somehow this is how it was stated in the real case by Applebaum and Chazelle, so we looked at the same problem. But yeah, so in the real case, so if you look at point hyperplanes, then it was proved by, again, Applebaum and Chazelle, that if G is an incidence graph of M points and hyperplanes, and we assume that the incidence is at least epsilon M. So but here we not necessarily think of epsilon as a constant. It can be a function of M and N. This is somehow more natural to state.
We are now over the reals.
Yes. Yes, so now this is in RD. The incidence is at least this, and we assume that epsilon is not too small, so this is necessary. So this is at least m to the -1 over the -1. Then the size of this largest bipartite graph is at least some constant, the epsilon to the d -1 times m times m. So interestingly, when epsilon is a constant, we can find a really huge bipartite graph, almost covering all the vertices. But this is very good even when epsilon is is not too small. And unfortunately here we have the same issue that we don't really know how good this theorem is. So there aren't really examples achieving this.
So you cannot, even if epsilon is a constant, if you have a constant fraction of the edges, then you actually have a constant fraction of your graph is a complete bipartite.
Yes.
That's pretty amazing, yeah.
Yes. Yes. So it's not completely surprising. So in some level, this is related to the Lagrange conjecture, because if you look at the adjacency matrix of points and hyperplanes, this is a low rank matrix. So this is a rank D matrix. And this says that so now instead of having zeros and ones, you have like zeros and stars. And this shows that if you have many zeros, then you can find a complete all zero. Yes, and here there was a related result of Singer and Sudan, which is recent, where they show that this RSG is at least omega. So now the important is that this does not depend on the epsilon to the 2d times m over d. So this shows that when epsilon is like 1/2, so your incidence matrix is half of the zeros, then you can find a complete zero submatrix of size roughly 1/2 to the d. So this is worse in epsilon, but they cared really about the dependence of d because of these possible applications for the Lagrange conjecture. And here actually in this regime, there is a conjecture of Lovett that this should be actually, so when epsilon equals half, then maybe this should be omega, something like 1/2 to the square root d times mn, some constant square root d mn. So this is not known, and this is conjecture proposed by law.
So this is over R, right?
Yes, this is over.
Why is it why is it just ones and zeros?
This is not ones and zeros. This is zeros and stars, basically. So 0 and non-zero.
But the Lagrange conjecture, it's the main point is that it's 0 and 1.
Yes, but in Lagrange you conjecture here log d, polylog d. But actually there is this, so in Lovett's paper about the Lagrange, he proposes this conjecture where you have a 0 star matrix. And here the square root is actually right. So there are constructions which show that you cannot improve this. So it's interesting for Lagrange, you can't improve this, but you don't have a matching bound. But this, you have a matching bound, but you can't prove this. We have this. Yes. So let me state what we proved. So again, we looked at the same problem over arbitrary fields. And we show that so G is incidence graph. So again, we have m points on hyperplanes. And now we are in after the D. We have again number of incidences is epsilon, and then we get that this RSG is at least some constant d times epsilon d minus 1 times m, and if epsilon is at least some 100 times the maximum of to the minus 1 over d minus 1 and to the 1 minus d, so it's not too small. And it's actually epsilon, and if epsilon is less than 1/4 over the same bounds. So there is this kind of jump here.
So it's roughly the same as in the reals.
Yes, so here we get the same as the reals. And yeah, so here let me put that m is less than n. If m is greater than n, then you can just switch everything. And yeah, and again, these bounds are sharp. So we not only recover the same bound as over the reals, we can show that over finite fields, they again sharp in this sense that for m and epsilon, I can find this field. And then the proof is, again, the same. We look at graphs which have this forbidden induced pattern, and then we use dependent random choice to carefully analyze, and we get these bounds. And even our dependence on these is reasonable, so we also get some exponential dependence on D. So I have a bit more than 5 minutes left, so I don't know if I should start anything. I don't think it makes sense to just dump more results on you. So, or if you want, I can, because the next one would be some algebraic geometry. Okay, just very roughly. So we also looked at the problem where instead of hyperplanes, we look at just the incidences of points and varieties. And again, without defining what varieties are or any of this, we prove. Let me write what a result is. So theorem. So if P is points and say V, so this is n varieties. So now let's say we work in RD, so now I use this capital D. Because now I will use D, so each of degree D. So whatever degree of varieties and each of no, sorry, each of dimension D. And each of degree at most some delta. Now if the incidence graph, so this GPV, again is KSS3. Then we get that the number of incidences is bounded by some constant depending on the dimension, the degree, and S times m to the D over D plus 1 times n plus m.
This is in R.
No, this is in F.
So there's this paper of Fox and et al. From a few years ago that does this for R, right?
Yes.
It's the same type of result?
No, so I can write up their results. So just lack of time. So what Fox, Bach, Schaffer, Suk, and Zaltmut is the bound. So m to the minus 1 times s. So somehow their exponent depends on s. ds minus 1 plus epsilon, or any small epsilon times n times d to the s minus 1, ds minus 1 plus m plus m. So this is in RD.
So you improve their result basically because yours is over any field. Right?
No, but their bound is stronger.
Oh, it's
So-
stronger.
So actually when s tends to infinity, these exponents tend to exactly this. So for large s, they are virtually the same.
You don't have the epsilon.
Yes, but there, I mean, epsilon is just a little one. And also, So there, it's really the dimension of the host space. And here we have the dimension of the varieties. So somehow our bound does not depend on the dimension of host space at all. It only depends on, not even the constant. It only depends on the dimension of the variety.
You can always map it down to like one plus the dimension of
So it
the
doesn't matter. I wasn't sure about this.
generic projection.
It depends on what assumption. Are they only assuming KSS3?
Yes.
And you can, yeah, I think I safely project it down to.
So, okay, then it's the same. So I wasn't sure that if you are over finite field, then maybe some issues, but
If it's large enough.
yeah.
Linear projection, you mean, right? Yeah.
Yeah, but again, this bound is based on like, so this uses the good and Katz polynomial partitioning, is also geometric. Our proof is we find a really huge bipartite graph, which we can form it as an into subgraph. But that bipartite graph, which I will not define, will have the property that on one side every degree is at most d+1. Now it's a well-known theorem in extremal graph theory that the extremal number of such graphs has exactly this bound. So we use the dependent random choice to extend this, that even if we forbid them as induced and we assume it's KSS3, then we can recover the same bound. And this is how it's proved. And yeah, so now I don't try to start anything new, so let me stop here. Thank you for your time.
Question? You have similar matching row bounds using variety basis for this?
Yes, exactly. So here actually you can just take random polynomials and their zero sets works.
Ah, you've done it explicit, yeah, okay.
Yeah.
No question. All right, good, thanks.